Hi there. The purpose of this video is to ascertain by experiment the value of leakage current and leakage resistance through physical capacitors. All physical capacitors will have some sort of leakage current through the dielectric. Now that is anticipated to be in the region of microamps or less than microamps, and we're going to prove that by experiment. We're after orders of magnitude here rather than getting the values down to individual ohms. So capacitor circuit could be modelled, capacitor component could be modelled by this symbol or circuit here. Ideal capacitor, two metal plates. Once it's charged up, there will be no current flow in this path. R series will be very low. However, there will be leakage resistance to reflect the current that will flow through the dielectric. It's anticipated that this leakage resistance will be in the region of hundreds of megohms and above, but we're going to prove it by experiment. So what we've got is a capacitor, and we've got the leakage resistance here. If we put in voltmeter or scopes, the issue with these meters is put any meter into a circuit, you're going to impact the original circuit. We want to minimize the impact. These meters ideally have infinite resistance, but they don't. It's likely they will have resistance in the region of megohms. So we don't want these values to impact the leakage resistance of the capacitor, and we'll prove by experiment in another video the actual internal resistance of these test instruments. So at the moment, what we've got in the circuit is, for reference, there's a 10 megohm resistor here. It's brown, black and blue, so it's 10 megohms. We've got a 10 volt supply, and we're measuring millivolts across the 10 kilo ohm resistor to measure small current flow. So we do have this voltmeter in here, so we're measuring the voltage across here, and by Ohm's law we can work out the current flow. So if we've round this off to 10 millivolts and we have 10 meg ohms, then what we have is 1 microamp flowing. Now 1 microamp at 10 volts shows that this resistor is 10 meg ohms. So we're using that as a reference. What we're going to do now is high voltage capacitor that's been taken out in a previous video of a microwave oven. 1 microfarad capacitor here. This actual capacitor has got a 10 megohm physical resistor connected in parallel so that it can be safely discharged when the power is switched off. That is not the leakage resistance of the capacitor, which is likely to be much higher. So this has got a physical 10 megohm resistor connected across it, and we can actually see that the current hasn't changed much from our reference 10 megohm resistor that we've previously done, showing it's in approximately 1 microamp, and it does appear that it's in the region of 10 meg ohms as a reference. So that is the high voltage capacitor. So what we'll do now is, in its place we'll put in non-polarized ceramic or possibly plastic dielectric in here. And what we can see on the voltmeter, the current has gone down to 0. Now this meter is on the 200 millivolt range. It's got a resolution down to 0.1 of a millivolt resolution on here. So if we do the math, then we can say that based on the maths, that if we're not measuring any current flow with this capacitor, we've got a resolution of 0.1 millivolts across the 10 k ohm resistor. That means that the current flow has to be below 0.1 microamps. Now that then means, by Ohm's law, that the leakage resistance of that capacitor has to be greater than 10 volts divided by 0.01 microamp, which is greater than 1000 megohm, which is greater than 1 gig ohm. So the leakage resistance of that ceramic capacitor is greater than 1 gig ohms. So that is what you would expect. It's an extremely high value. Let's change the capacitor type to this white one here. So it's going to have a different dielectric material. And if we look here, if we look over here, yeah, it's going down to 0 again. So again, the same with this capacitor, we can say that the leakage resistance is greater than 1 gig ohm with that type of capacitor. So these are non-polarized capacitors. Let's just try another non-polarized capacitor. They're all 1 microfarad, and let's see, it goes down to 0.0. Okay, so again, similar, we can say that the leakage resistance is greater than 1 gigs. However, if we go to a polarized capacitor, and we need to plug it in the right way round, Tantalum polarized capacitors, that's the negative and the positive, and let's see what current flow we get now. So what we've got now is a measurable current flow. Yeah, it's not 0. It's not 0. It's gone down. Yeah, okay, it's jumping between 0.1 and 0.2. Yeah, so what we'll do is we'll take the 0.2, that's 0.2, 0.2 millivolts. So if it's 0.2, and score that out there, we've got 10 volts divided by 0.02 microamps. So if it's 2 millivolts and we've got 10k, that means then we've got 0.02 microamps, and that means that we've got a resistance value of approximately 500 megs ohms, because we've now got measurable voltage and we've got measurable current. So if we've got 0.2, that does come out to be in the region of 500 megohms. So what we can say is, with the polarized tantalum capacitors, they do have a lower value of leakage resistance compared with the non-polarized ceramic or plastic dielectrics. So in summary, non-polarized ceramic or plastic dielectrics have very, very, very small leakage currents through the dielectric. However, the tantalum ones, the polarized capacitors, do have measurable leakage current. However, it is still in the region of approximately 500 megohms. So these capacitors will discharge, self-discharge, quicker than the non-polarized ceramic or plastic dielectrics. I hope that's been useful. I'll end the video here, and another video will actually show by experiment how to measure the internal resistance of meters. Thank you.